My name is Lefteris, and I have the honor of leading Beyond Robotics for participation in the European Rover Challenge 2026 in Poland. This marks our fourth year journey following our participation in the past 3 years. This year, we're developing TALOS 2.2, our most reliable and technically refined rover so far. The rover itself is developed by specialized subsystems in mechanical, electrical, infrastructure, navigation, arm, and science, each led by dedicated team leaders. Alongside our drone team develops the aircraft vehicle, while our marketing, graphics, social media, and HR teams make sure that our work is communicated, organized, and supported.
Beyond Robotics is organized on a systems engineering approach in two main technical systems, the drone system and the rover system.
The systems engineering role revolves around 4 core areas: the management of requirements, risks, assembly integration and testing, and the concept of operations, as well as the preparation of all the deliverables for the European Rover Challenge. While the rover may appear similar to previous iterations at first glance, significant improvements have been made that considerably strengthen our system. One of the most notable component upgrades was the introduction of a waterproof 3D printed electronics enclosure, enhancing the protection and reliability of the onboard electronics. On the software side, both the autonomous navigation system and the robotic arm control software have been substantially refined, resulting in more robust and precise performance. These are just some of the advancements that will allow the team to execute operations more quickly and efficiently, with the goal of achieving maximum points across all tasks.
This year we had one clear goal: to optimize our rover's existing architecture. Instead of starting from scratch, we focused on identifying and resolving specific performance bottlenecks to improve efficiency while keeping the system reliable. We designed a dedicated power transmission mechanism between the wheel axle and our 3D printed wheels, addressing mechanical play and torque inconsistency from previous testing. We designed and manufactured a custom electronics box with thermal management as a core priority. Through thermal simulations, we determined the optimal placement of each component, keeping temperatures under control. A forced airflow system with fans at the inlet and hexagonal outlet vents handles ventilation, while an internal shelf and mounting table create a clean, accessible 2-level layout. We fully redesigned the rover's cab to include dedicated configurations for the drone landings platform. Custom 3D printed hinges allow quick, tool-free access to the electronics for faster field inspection. Our 3D printed wheels were deforming during downtime due to heat and static weight. We solved this with targeted repair kits for the honeycomb cavities and custom support stands that keep the rover elevated when not in use. Finally, we established a structured inspection routine across all mechanical systems, repeated after every testing period to keep the rover competition ready.
For the Payloads subsystem, our main mission was to move far beyond simple functionality. We focused on iterative evolution through extensive field testing. By pushing our system to their limits, we tried to maximize the performance of our 2 core components, the drill mechanism and the robotic arm. Starting with the drill, we integrated custom 3D printed bases to increase our maximum drilling depth within the soil. To optimize the robotic arm, testing revealed the need for better performance. We collaborated closely with the electrical and software subsystems to fine-tune motor communication for peak torque and integrated new metal 3D printed couplers at the joints for increased power transfer. Additionally, we installed end stops on every joint to establish a reliable homing position. Finally, we increased the structural integrity of our end effectors. The probe gripper was specifically redesigned to ensure the collection of probes, whether they are upright or laid flat. To handle the increased mechanical loads, we transitioned our 3D printed gear mechanisms from standard PLA to PET-G carbon fiber, providing the robustness needed for high repetition start.
We've elevated the TALOS 2.2 software with high-performance features designed to redefine the user experience. This latest iteration integrates intelligent thermal management and precision pump control. We built advanced calibration routines for our entire scientific suite. By eliminating critical bugs in firmware, we've developed a more robust, reliable, and seamless system.
Our 6 degrees of freedom robotic arm is evolving into a more intelligent system this year, with major focus on repeatability and autonomous operation. Current development focuses on refining our reverse kinematic setup and integrating automatic homing, physical end stops for a more reliable startup. By layering computer vision and ML-based control, we aim to simplify complex tasks such as maintenance panel component detection and localization, and move towards fully autonomous manipulation.
TALOS 2.2 features a hybrid perception and localization system based on sensor fusion and visual SLAM. The platform combines IMU and wheel odometry data with a single depth camera, enabling robust environment perception and state estimation. In addition, GPS data is used as a fallback. Incorporating advanced autonomous navigation algorithms along with real-time terrain analysis, TALOS is able to evaluate the best path forward based on terrain traversability and obstacle avoidance. For mission supervision, map-based visualization methods have been developed.
Building on its proven success last year's competitions, our telecom subsystem leverages a high-speed 5 GHz ubiquity U6 mesh link for seamless ground-to-rover communication. By utilizing a dedicated antenna mast, we ensure near line-of-sight connectivity across diverse terrains.
The electronics team divides operations into two critical domains, high voltage and low voltage applications. This allows for a more structured approach to maintaining the rover's electrical integrity in extreme environments. Learning from critical errors during last year's competition, our team's primary focus for this year has been system reliability and overall robustness. Our new electronics box has been a major step towards that goal. Not only does it provide superior protection and cooling to the internal circuit boards of the rover, but it also gave us the opportunity to completely overhaul our electrical layout. Our high voltage team members, which are responsible for integrating this new enclosure, are actively inspecting and replacing any defective wiring or components in order to prevent future electrical failures. For our low voltage systems, we mainly focus on designing custom circuit boards for both new and existing applications. Specifically, we developed an improved mobility board centered around a TNG 4.1 microcontroller. This allows for high-speed communication with our BLDC drivers, providing the user with precise, low-latency control over the rover's movement.
The science subsystem is responsible for analyzing Mars geology and linking its terrain history to the potential existence of microbiolife. This year, our exploration area is characterized by glacial and volcanic features. At the same time, strong aeolian activity shapes the region, creating a unique interaction between lava, ice, and wind-driven processes. Our rover is equipped with a WEM to analyze atmospheric indicators, while also measuring ground temperature and classifying surface material. Finally, astrobiological sampling, combined with our geological analysis, will help us better understand the region and evaluate our hypotheses.
Meet Infinity 2.0. Our subsystem is comprised by a team of 6, and this year our goal was clear: refine what we built last year, make it smarter, and make it tougher. The foundation remains the same. What changed is the frame. We completely redesigned it using the generative design environment in Autodesk Fusion, replacing last year's X-shaped frame with a purpose-optimized structure driven by 5 real-world load cases, with mass minimization as the objective. The result is a 6-inch quadcopter frame 3D printed in PETG glass fiber that is 20% lighter and 10% stiffer than its predecessor.
On the software side, this year was about building a more capable and robust architecture. Our navigation stack runs in real time on the Raspberry Pi, powered by algorithms created on MATLAB and compiled as native code using MATLAB Coder, eliminating runtime dependencies and significantly improving execution performance on embedded hardware. Our AI-based detection system used for identifying mission targets, the probes, is fully operational and has gone through multiple rounds of real-world testing and iterative improvement. Alongside it, our Aruco marker detection, position keeping routines, and ground station GUI continue to serve as reliable tools for autonomous mission execution. Together, this upgrades with Infinity 2.0 to a new level of autonomy, reliability, and repeatability. The system has been validated through both simulation and field testing, and we're confident in its readiness for the challenge ahead.
So this is our project. This is our team. This is our family. See you in Poland.